Hi everyone, welcome to RPI Data Science. So remember last time we have seen meta-analysis of binary outcomes. Mainly we have seen actually meta-analysis of odds ratios. So we have pooled odds ratios together, and we have seen the effect estimate, like the pooled effect size, and also we visualize it in forest plot. Today we will continue on meta-analysis of binary outcomes. Particularly we will see meta-analysis of risk ratios. But before we proceed to that, we will do a small recap, and we will continue forward to meta-analysis of risk ratios. So first thing first, we will do a small recap as I said. So here we have, we've seen meta-analysis of binary outcomes. So binary outcomes are measured in relationship between exposure and outcome. It can be measured in odds ratios or risk ratios, hazard ratios, and other measures of binary outcome. So let's say here we have event, no event, and here on this side we have exposure. So that means the exposed group and then the non-exposed or control group. And here we have the event. So that means an event, the number of events on the exposed group, and the number of non-events on the exposed group again. And here we have the total number of the people who are on the exposure or exposed group or on the treatment side. And here this is a control side. On the control side we have number of events in the control group and the number of non-events on the control group, and this is the total. So to calculate odds ratios, odds is not a probability, as you know. So odds is a ratio of event or over non-event among the exposed group, and the ratio of events divided by no event among the control group. So that means A over B or C over D. That gives you odds ratio, and in other words it would be AD over BC. That's yeah. That's odds ratio, and that means odds ratio is not a probability. It's simply the ratio of an event divided by the ratio. The ratio of an event over non-event. But as opposed to odds ratio, risk ratio is a probability. So that means risk is the probability of an event among the exposed group. So that means A divided by the total, A over A plus B, and then the ratio of an event among the non-exposed or the control group. So that means C over C plus D. So that will be the probability of an event in the control group. So the risk ratio will be the ratio of the two risks. So that means the ratio of the ratio of the risk and event. The risk on the experimental group or exposed group. That means and then divided by risk among the control group. So if you divide that, you get risk ratios. But sometimes odds ratio may be an approximate measure of odds ratio may be an approximate measure of risk ratio. So there is a possibility, for example, when the disease is rare, then odds and risk ratios are approximately equal. There is also a conversion factor where you can convert odds ratio to risk ratio. So the way you convert it is this way. So you have risk ratio equals odds ratio, and you divide odds ratio by this conversion factor. And this conversion factor is 1 minus, this is P, that means the prevalence of the disease, plus again you multiply the prevalence of the disease by the calculated odds ratio. Then if the disease is rare, so that means this value, the limit of the prevalence is close to 0. So that means 1 minus something really close to 0 would be 1, and something which is really close to 0 times odds ratio would be cancelled out 0. So that means this value would approximately be 1. So 1 point something, 1.00 something, or something like that. So that means if you divide the odds ratio divided by 1, it gives you exactly the same value. So that means when the disease is rare, risk ratio would be odds ratio would be approximately equal to risk ratio, or odds will be a good measure of approximate measure of risk ratio. That's common in when the diseases are rare, for example in cancer or something like that. So sometimes when the disease is rare, you will be able to combine risk ratio with odds ratio altogether, and you can define your effect size measure in your Metabin calculation. So Metabin, coming to Metabin, I think I remember I showed you this kind of graph here. So here are some of the functions that we need when we pool, when we do meta-analysis. So we have seen last time with Metabin, we have also seen with metagen. So if you really get the values of the number of event, the number of control group, and the number of the number of events, no event, those A, B, C, D values, then you can use Metabin Metabin. Otherwise, you can also manually calculate odds ratio or risk ratio, and then from there you can use a metagen function. So metagen, so that means you pre-calculate the odds ratios or risk ratios, and then using the metagen function, you can pull them all together. Yeah, so the other thing you need to calculate, to pool binary outcomes or maybe risk ratios and odds ratios is you need standard error. The standard error would be 1 over a. For example, standard error in odds ratio would be 1 over a, the square root of 1 over a plus 1 over b plus 1 over c plus 1 over d. That means reciprocal of all of these values, summation of the reciprocal of all of these values, and then you take that value under the square root. That means you get the standard error of odds ratio. But if you want the risk ratio, the standard error of the risk ratio would be the number, because you take the probability of an event, so that means 1 over a plus 1 over c, then you subtract the variance here, so that means 1 over the total, and then you subtract again that, and then you take that one in the square root. I will show you that one in a minute. So this is a formula of risk ratio, so that means EE, that means the number of events in the experimental group divided by the total, that means probability of disease in the exposure group and probability of the disease in the control group. And to calculate the standard error, because you need this value for pulling together, so you need the standard error. So to calculate the standard error, what you need is the square root of 1 over the event, that means the A in the 2 by 2 table, divided by, plus 1 over that event in the C, so that means the number of events in the control group, and then you take you subtract those, the total population, this NE and NC. Then with that you calculate the standard error of risk ratio. If you have these values, you can simply pass them via log odds ratio, log risk ratio. Then you will be able to put them together. Why you pass them in log odds is because risk, odds and risk, odds ratio, for example, odds ratio is always greater than 0. So it doesn't go less than that. So it's always greater than 0. And so that's why you have to, it's a skewed distribution, skewed to the right. So that means you will have to transform it. So the same is to correlation, because it's always between -1 and 1. So that means the distribution is skewed within this range. So that's why you will have to transform them to get normally distributed, and pooling will be easier. Yeah, so we will go up and reproduce the things that we have done last time. So let me reload some of the libraries. These are the libraries that we need, Meta4, in case we need some of the functions that we find from Meta4, but we will mainly use Meta and then deploy. So I will rerun this code, and then I will simply load the data. The data is, again, we will use the same data set, which is in the meta-analysis in our book. I will put probably I will put the link in the description of the video if anybody wants it. And let's have a look how the data looks like. So the data looks like this. So we have the number of events in the experimental group, and the number of events, no event in the experimental group, and here are the events control group, and then no events in the control group. So once you have all of this, you will be able to calculate the standard error, and you will be also able to calculate odds ratios or risk ratios. So that's what we have. So here we have already done this actually last time. So I will simply show you how to recalculate standard error. An odds ratio. For example, for this we are calculating standard error for this particular study. For this one. So if you run this with function, or you can also use something else to calculate, so that would be the standard error of that study. But if we want to calculate the odds ratio, we'll do it differently. So again, so this is again what you can do using the the same method, but using deployer. We are taking study Hazel. Let me rerun it, and we will see that value here. So we are putting it here. But now, because we need log odds ratio, so to be able to meta-analyze the values, we either need all of these values here, and we simply pass with Metabin, and the Metabin will be able to calculate it for us. Otherwise, we can also use metagen, and if we use metagen, we will have to manually pre-calculate the odds ratio values, and we take that one to the logarithm, so we will be able to calculate log odds ratios, and then again we will have to calculate log standard error, and the standard error or the upper and the lower confidence interval. So I will simply recalculate all of them here by reproducing. This is actually that we have seen last time, so let me simply rerun this, and then we will be seeing the head of the data. So here we have the log odds ratio and standard error, and also log odds lower and log the upper confidence interval. And after that, we can simply pass. We can either use the Metabin or metagen. We have now luxury of two functions. We can either use the Metabin function. If you use Metabin requires these arguments, and also you have to define the effect size metric, that's odds ratio. And also you need to define the method. We are using inverse variance here, and the rest is simple because we want to use random effect meta-analysis. So that's why I'm taking this fixed effect meta-analysis off, because I recommend everyone to just do random effects meta-analysis. Fixed effect is just for theoretical understanding. You can use it, but otherwise, if you want to pull, even if heterogeneity is 0 or something, you can still. I recommend still using random effect meta-analysis, unless the study is unless your meta-analysis is from individual participant, not individual participant, like from the same cohort but different studies, which usually is not common. So in that case, you can use a fixed effect. Otherwise, really unlikely that studies are highly homogeneous in terms of several dimensions. So let me rerun this, and then we can simply pass it in the forest function, and then we can have the plot. Yeah, so this is odds ratio, and then let me rerun that again. So it's still showing. Oh yeah, okay. So now we have a problem because the plot is not showing us. So I need to do something. I actually have a code somewhere to yeah, so I need to rerun this code because the Jupyter, I mean, for you it will not be a problem because if you are using RStudio, I'm not using RStudio, that's why I need to arrange the plotting width and height. I'll just use this report library, and then I will use options. We'll set the width 10 and the height as 8, and I simply rerun it and go back to that previous plot and rerun it. So if I rerun, I should be able to now see the plot clearly. So here you go. We have a pooled odds ratio of 1.36, but when you see some of these values, I-square is 41%, which is not really, it's not so much heterogeneity, but still there is some sort of heterogeneity. Yeah, so here we have 1.36 pooled odds ratio of, and then you see the confidence interval 1.07 to 1.73. So here we already have, so that means we have so that means we have we just pooled odds ratios. But if we want to do risk ratio, what we can do is we can either use Metabin and change this to risk ratio, or we can also simply use this update meta function. So let me remove that one. Update meta. So if you update meta and you simply change SN to R, that means the model we already have it previously for odds ratios, and if we simply use update meta function, and then we simply M1, and if we change this SM, it used to be in the previous plot it was OR, that means odds ratio, but now we are changing it to risk ratio, so that means the Metabin will be calculating, will be pulling it for risk ratio for us. So if we run it, so that means we will be able to get the pooled forest plot. So here we have 1.36, that means odds ratio, but now the value should be a little bit smaller because odds risk is probability, and probability is calculated from the total, so that ratio will be a little bit smaller. So that's why we have the risk ratio is smaller than what we saw in the previous for odds ratios. So we have 1.12, and the confidence interval is showing excluding the null point, so that means it's significant, and the heterogeneity statistics is also small. So anyway, the exposure is increasing the risk of experiencing, I mean the risk of having the disease. So that's what we can do, what we can see in this plot. The other thing, the other way you do it is like by using metagen function. For the metagen, if you remember, we already have some data. So if you let me show you the head of our data. So for the head of the head of our data is df, and if we run this, so you can see. So for the metabin, we only need these ones, and then the rest is calculated by the by the metabin function. But for the metagen, what you need is you need odds ratio. You will have to pass it in the logarithm, but we already converted it to log odds ratio, and we can have either standard error or the upper and the lower interval values for the log odds ratio. So that means you need either the standard error or log lower and log upper. So if you don't supply standard error, the metagen function will use these values. But if you don't supply the confidence interval, but you supply the standard error, the metagen function will only use the standard error. So sometimes in studies, in your, when you collect the data, some studies may report confidence intervals, others may report standard error. This is not a problem for metagen. So you can supply it the standard error, you can give it standard error or log risk ratio, I mean log odds ratio and upper, then it will be calculated for it. It will calculate it for you. So here I'm defining the log odds ratio as the effect size. And also here I'm defining the standard error. I'm giving it the effect size estimator as odds ratio, and giving it the lower and the upper. I give it all of this just in case. So if there is missing value in here in this part, or if there is missing value here, so if there is missing, that means if the confidence interval is missing, so the metagen function will use the standard error, but the standard error is missing and the confidence interval is reported, so the metagen will use the upper and the lower confidence interval. I think this is really one of the key advantage of the metagen function. So we simply run it in metagen, so that means then we will be able to see the forest plot, so using metagen. So if you remember, our odds ratio was 1.36 using the upper method, and the I-square was also 44%, so 1.08, 1.73. Probably there may be a small rounding error because we are manually calculating it. So maybe if we go back, 1.07, 1.73, our interval down here is 1.08 to 1.73. Otherwise, everything else is the same. So we'll do the same for we cannot do this for update meta because the risk ratio and odds ratio are calculated differently. So we will have to change a few things. The first thing is we will have to calculate log risk ratio. So we need to calculate log risk ratio, actually log risk ratio for our data frame, and then we will also have to do log the upper and also standard error and things like that. For that, we will have to rewrite the previous function, and then we can use it for that. So for that, I will have to copy this, and then I will change a few things. So for changing a few things, I will copy this and scroll down and bring it down here. Yeah, I'll bring it here, and then I will have to change a few things here. So the first thing is I need to change this to risk ratio, and then I will have to change this one, log risk ratio, has to be this one to the total event because it's so that means it will be experimental group. The number of events in the experimental group will be divided by the total. So I will have to remove this subtraction. Again, I will again remove, so it will calculate the probability. So now I get the log risk ratio from these values. Now I need to calculate the standard error. For the standard error, what I need is the number of the ratio of, that means the reciprocal of the square root of the reciprocal of this event in the experimental group, and then I will need to have the other one. So the other one would be here 1 over even in the control group minus there will be minus then I will subtract this 1 over NE and again minus again okay, minus again. That is a formula actually, the formula for standard error of risk ratio. So that will be the formula. So you have square root of 1 over E plus 1 over C. So that means the event, the number of the reciprocal of the number of events in the experimental group, and the reciprocal of the number of events in the control group minus the total. So then with that you will be able to calculate standard error. Once you get that, calculating the standard log lower and the log upper is easy, because that's confidence interval calculation. I will simply change a few things. I will add risk ratio here, and again risk ratio, and again I will have to change this log odds ratio to actually I will need also change the standard error risk ratio. Let me just change this, and again here standard error. So now I have log risk ratio, I have standard error of the risk ratio, then I have the log lower calculated by this, so that means the confidence interval, the lower and the upper confidence interval. So now I have everything, then I will take a look at my data. So there seems to be an error somewhere. Okay, it should be somewhere down here. Yeah, that one seems to be right. Okay, this is wrong. So it should be square root should be okay. I don't use this bracket, so now it should be correct. Now let me rerun it again, and I should be able to get my data. Now everything is all right. Now let me see here of my data frame. Now I should see all of the values obtained. EF. So now I already calculated the log risk ratio, the standard error, and yeah. So these are the values that I need for using the metagen function for risk ratios, and then the rest is just passing the values. So now let me just use actually metagen. For the metagen, the first thing you need is TE. For the TE, what I need is log risk ratio. Let me define the data frame first, actually, because sometimes it makes it easier. Then the standard error would be standard error risk ratio, and log the lower confidence interval. So that would be log risk ratio, not log risk ratio. What did I call it? Okay, I called it log lower risk ratio. Lower risk ratio. Then I will simply again the upper confidence interval, the upper confidence interval. Let me take this down here so it will be more readable. The upper confidence interval would be log upper risk ratio, and then I will define my effect size metric, so that will be risk ratio. Once I have that, I can define my study label. So that should be actually, what was that argument? Stud lab, I think, because I want to label in my forest plot, I want to see these ones instead of like with numbers. Stud lab equals study, should be like this, and then after that I think we should be fine. And then once we have that, we can pass it to the forest function, and then we will see the forest plot. It seems I seem to have some error. Log risk ratio not found. Okay, this one is log RR, not log hyphen R. Okay, now I should be, it seems I have another error here, log risk ratio not found. Isn't that this one here? Okay, let me just copy this. Log risk ratio. Okay, let me go back again, and then let me rerun it. That's what we have. Something wrong. Yeah, I got a problem. It's here. I should define data, not data frame. So data equals data frame. Now I should be able to get the forest plot. So there seems I don't seem to have the study. What is that? Let me have a look again. What is that called? That variable is study. Okay, so it's a small letter s. So now it should be able to work. So now it's running. there you go. So we use the metagen function to calculate the risk ratio, and now it's also displaying the fixed and random effects model. And now let me just turn that off, this fixed effect model. I don't need that. I will simply fix it false. Now I should be able to get that thing off. So now you can see the risk ratio of the pooled risk ratio of the random effects model using the metagen function. That means 1.1 to 1.03 to interval of 1.22, and I square is 35%, which is exactly similar to what we did using the Metabin function. Using the Metabin, if you remember, we have done it here. So down here. So here we have 1.03 to 1.22, and here we have 35%, and tau square is actually really low also. Yeah, so these values are identical. So we recalculate. I mean, you can choose. I prefer to use metagen because you don't get these values reported from the studies. So you usually get the odds ratio and confidence interval, so odds ratio and standard errors, or risk ratio and confidence interval or standard errors. So that's why in that case, metagen function is really handy instead of these values, because you don't get these values, and often the reported odds ratios and odds ratios and risk ratios, they are adjusted. So if they are adjusted, you can't also easily calculate them from these values because they are adjusted. They are adjusted to some other variables. So in that case, you will have to calculate by hand the log odds ratio, and after that you simply pass it to the metagen function, and then the rest is done by this metagen function, which looks like quite easy for me. Yeah, so that's all for today, and in the next session we will continue further on meta-analysis of binary outcomes, and we will see other topics in meta-analysis like meta-regression and many other issues like heterogeneity and publication bias and things like that. For today, thanks. I hope you will come back. Ciao. Enjoy meta-analysis.